We're going to shift gears a little bit and talk about Newton's universal law of gravitation. We know that if a man stands on the earth, he is going to feel the force due to his weight in the downwards direction. That's going to be mass multiplied by gravity, where this, gravity was, this was an acceleration due to gravity of 9.8 meters per second squared, and it was always down towards the earth. Now we're going to take a closer look at this force due to gravity and where does it come from. Newton realized that this force must come from inside the earth. Regardless of where you travel on the earth, you're always pulled down inwards to it. And also, he had already came up with Newton's third law that says for every force there must be an equal and opposite force, and he reasoned that the earth is pulling down on you, you must also pull down, or you must also pull the earth up towards you. So he also realized that this is what kept the moon in orbit, and he started to look at planetary bodies. So I've already mentioned that it's one half of the third law in action-reaction pair, and it turns out that if there's a huge disparity in the masses, for example, the mass of you might be 100 kilograms, the mass of the Earth is going to be 10 to the 24 kilograms. Huge disparity in masses. The reaction force of you on the Earth is so small that you could say that it's detectable. But he reasoned that if the bodies were more close or equal in mass, then this could be detectable. So he started to take a look at the Earth-Moon system. The Moon is held in orbit around the Earth because of gravitational forces of the Earth acting on the Moon. The other half of the action-reaction pair is the gravitational force on the Earth exerted by the Moon. Where do we see that? I used to live in the Hampton Roads area, and we would see the tide. That is the gravitational force exerted on the Earth. That's due to the gravitational force exerted on the Earth by the moons, shifting the tides around. So Newton went about trying to come up with a relationship to describe this gravitational force, and he reasoned that it must be proportional to both masses of the objects that you're interested in. And he looked at planetary orbits, and they had a reasonably good idea of the distance between the planetary bodies, at least for the period, and he realized that the force must decrease inversely proportional to the square of the distance between the masses. And I'll remind you, this is pre-computers. He was doing all of these squares and inverses by hand, and he was crunching a lot of data. And at the end of the day, he came up with a relationship that says the force of gravity is going to depend on the mass of one of the objects that you're interested in, the mass of the second object that you're interested in, as well as their distance between them squared. This big G right here was an empirical constant to make the proportionality an equal sign. This big G has a value of 6.67 times 10 to the negative 11th. These units right here make all of these masses and radiuses work out. Keep in mind that this is not equal to little g, which is 9.8 meters per second squared. So we can perhaps consider an Earth-Moon system where here we have our Earth, and over here we have our Moon, and we can write the force due to gravity if we know the mass of these two objects. Mass of the Earth, mass of the Moon. Don't forget my big G right there. And then their separation squared. Let me just say real quick that the separation squared is not surface to surface, but center to center. This would be the force of the Earth on the Moon and the force of the Moon on the Earth. It's going to be equal forces here. Opposite directions. So this is going to be the force of the force on the Moon due to the Earth, equal and opposite to the force on the Earth due to the Moon. Both of them are going to be this force right here. Now, it's always amazing the methods that people come up to measure this constant G. Newton, did it using tables on planetary objects, but it turns out you can actually measure it in the laboratory. It's got a famous experiment right here, Cavendish, and essentially all he had was two masses with a thin rod, all of this suspended by a very, very, very thin fiber, and just a little mirror right here. The laser light shined off the mirror onto a scale on the wall, and then you bring in from the side this other, roughly similar mass A, and you know what the distance is between them. Then this mirror is there's going to be a force of attraction. It's also going to be a force of attraction right here. It's going to swing the rod over, and then the laser is going to, the mirror is going to turn. The laser is now going to be reading over here on the scale, and we could calculate what the force is. We know what the masses are, so we could actually go ahead and calculate out the gravitational constant G right there. Thinking about Newton's law of gravitation with in response or in context of what we already know, if I have an object that's on the Earth, up until this point I've said that it's going to feel a force due to gravity. It was equal to its weight, which was equal to its mass times gravity. What Newton's law tells you, based on what you've learned in this chapter, is it's going to feel a force due to gravity that would be equal to the mass of the object, the mass of the Earth, and their separation squared. These are really the same equation, it's just this is more of a generalization. We can actually determine G using Newton's law of gravitation simply by saying these two forces must be equal to each other. So the mass times gravity is equal to the mass of the Earth divided by their separation squared. Put my big G off to the side there. So the masses are going to cancel out, and we can say that the acceleration due to gravity is going to depend on big G, the mass of the Earth, and the separation squared. So thinking about the Earth, it's actually not a perfect sphere. The radius, the distance you are away from the center of the Earth, can actually change. If we looked at New York, which is at sea level, gravity is going to be 9.8 meters per second squared. But somewhere like Denver or Pikes Peak, this radius right here is a little bit larger now. Correspondingly, the value for g is lower there. If you think about something like the Olympics are always held at sea level. There's a reason for that. It's because they don't want the athletes to have an unfair advantage and have lower amounts of gravity to to jump against, shall we say. When we launch a satellite into orbit, you might ask yourself, what keeps it up? And it turns out that it is its tangential speed that is keeping it up into orbit. And what we're really doing is we're using the two concepts that I've talked about up till now, the gravitational force and then the fact that there's some radial acceleration. And it turns out that the gravitational force is providing the radial acceleration for the satellite. Here's the satellite right there. It's going to feel a force down towards the Earth like that. So mass multiplied by the velocity squared divided by the radius, that must be equal to this gravitational force right here. And it turns out that if we launch a satellite with a speed of 2,700 kilometers, that satellite is going to go into a nice perfect circular orbit. It's always going to have that velocity of 2,700 kilometers per hour. There's essentially no friction up there, and it's balanced by the gravitational force right here. If we launch an object at 30,000 kilometers per hour, it's going to go in an elliptical orbit, kind of like that. It's always going to have a velocity of 30,000 kilometers per hour. The radius changes a little bit, but in general, gravity still balances it out. There is some velocity that we can shoot a projectile at. Turns out that it's 40,000 kilometers per hour, such that the gravitational force cannot balance that guy out. There's just simply not enough mass on the Earth to do that. And in that case, the object's going to escape Earth's gravity. So what's going on here, once again, is we have our satellite that's moving at some velocity right there, and if gravity did not exist, this object is going to continue to move in a straight line at a constant velocity forever and ever and ever and ever. But gravity is providing this force. It's a downward center facing force right there, force due to gravity. That gravity is going to provide the acceleration such that at some point over here the satellite's going to have a velocity like that. It's going to have a force downward in that direction, and so on and so forth. Essentially, you can think of a satellite as simply continuously falling towards the Earth. However, its tangential speed is keeping it up, and the Earth is going to curve away from it. If an object didn't have enough tangential speed, then it could crash down into the Earth. So thinking about satellites, if objects in orbits, they're said to be weightless. However, that's a little bit of a misnomer because they always have some gravitational force acting on them. Satellite or astronauts on the ISS, for example, they have 95% of their weight that they do on Earth. What they don't have is they don't have a normal force acting on them. They're in the ISS, they're going around the Earth, they're continually falling, the satellite is also continually falling, and nothing is going to provide that support force for them to impede their acceleration. You can kind of think of that if you're in an elevator and this elevator is not accelerating, it could be at some velocity, then you're being supported by the floor and you're looking at this scale and you're seeing that it's reading the weight of this bag. If the elevator was accelerating upwards, you have a larger support force going upwards from the floor. You feel like you're heavier when the elevator is accelerating upwards, and you read a larger weight off the scale. If the scale breaks and all of the acceleration is now downwards at 9.8 meters per second squared, the elevator is accelerating downwards with that acceleration, you're accelerating downwards with that acceleration, so there is going to be no support force from the floor. Similarly, for the scale, there's going to be no support force. It's going to read a weight of 0, kind of like an apparent weight. That is the feeling of the experience of weightlessness that we talk about in space. And we can experience that, in other areas of our life too while we're on Earth, even for just a very brief period of time. For example, if you ski and you go off a cliff, you have no support force holding you upward, you're accelerating downwards, due to your weight. You're in free fall and you have apparent weightlessness, neglecting air resistance, of course. Last but not least, I'm going to talk about a very special type of satellite motion. This would be planetary motion. Planets are essentially the same as satellites. And a fellow by the name of Johannes Kepler came up with 3 laws to describe these, to describe planetary motion. I'm going to talk about them in these next couple of slides here. The first one of Kepler's laws says that planets are going to move about their sun in an ellipse, and the sun is going to be at one of the 2 focal points of the ellipse. So it must be either here or here. And this is actually a fairly recent discovery in astronomy, because in our solar system, most of the orbits are nearly circular, which has a focal point near the center. This is a special type of ellipse called a circle, but in general, this is the one that must be applied, because not all orbits are going to be circular like they are in our solar system. Kepler's second law talked about how fast objects are moving around the sun based on where they are relative to the sun. So here we have the sun. It's at one of the 2 focal points in the ellipse, and our planet is, cruising around the sun. So Kepler said if you take a line between the planet and the sun, you draw an imaginary line right there, and then you wait a certain amount of time, let's just say 1 month. Now you take that same planet, you draw a line to the sun, an imaginary line, and you look at this area right there. I'm going to call that area 1. Now, later on in the orbit, let's draw a line between the planet and the sun. Same amount of time, 1 month. Draw another line between the planet and the sun. And this area, area 2, must be equal to the first area right there, area 1. So that's Kepler's second law, that a line between the planet and the sun is going to sweep out equal areas in equal times. And this is accomplished by the fact that over here, close to the sun, the planet's going to move faster. Over here, the planet's going to move slower. And last but not least, Kepler came up with a law describing a planet's period and its mean distance from the Sun. What he did was he said that the period squared must be equal to a couple of constants, 4 pi squared g, and mass of the object that's being orbited. In many cases it's the Sun, so I put a s right there, multiplied by a cubed. This right here is going to be the mean distance from the Sun. And it was kind of amazing that Kepler was able to compile all of these periods and all of these radiuses and make this relationship happen, especially since we're talking about, you know, long before the computer era. I'll also say that Kepler's laws can be derived using Newton's laws. Newton's laws, I said, can apply to satellite motion. Kepler came up with his laws totally on his own, but they are consistent between the two. So, you know, it's good to have self-consistency between laws. Although, as time has gone by, there's been irregularities, or, you know, we could say wobbles in planetary motion that couldn't be described by either Kepler's laws or Newton's laws, and that actually led us to the discovery of other planets. For example, Neptune, and outside of our solar system, looking at irregularities in in the way objects are moving between the way that we expect them to move from Kepler's laws or Newton's laws. That's allowed us to discover other planets outside of our solar system. So just a summary real quick, I'm just going to page through it.